Okay, this is the video now on ionic compounds. And as we mentioned in the molecular or binary molecular compound video, don't forget this skill is very, very important. So we're going to teach you how to write the names of them. We're also going to teach you how to write the formulas. I'm going to do the formulas first and then I'll do the names. But again, this is a skill that's extremely important. You must master this, okay? And so make sure that you're working hard on getting this down. Okay, so again, we're going to write formulas for ionic compounds first. So obviously we're going to start with a name. And here's a very simple one which you should be familiar with, sodium chloride.
Table salt.
Exactly. So sodium chloride, table salt. First of all, how do I know it's an ionic compound? Well, because it starts basically, usually, with a metal. If it starts with a metal, that's a good indication that it is an ionic compound. In the previous video, although I didn't mention it at the time, those compounds generally would start with non-metals. So if it starts with a non-metal, you can pretty much say it's a molecular compound. But if it starts with a metal, you can pretty much say that it's an ionic compound.
You should refer to your reading that you have done before this video to know the designation between a metal and a non-metal and where you can find them on the periodic table.
Absolutely. Very good. Thank you, Mr. Walsh. So now, my friends, here's the deal. What we do is we write down the symbol and the charge of each ion in the compound. Sodium, Na+, chloride is Cl-. Now remember, all matter has to be neutral. So even though that this is a charged species and this is a charged species, when they come together due to the electrostatic attraction between the two of them, they're going to come together in such a way so that the number of positive charges and the number of negative charges are going to cancel each other out. And when they do, we end up with a neutral portion of matter.
Now remember from physics, opposite charges attract. So these ions are going to be attracted to each other in a chemical bond, an ionic bond.
Okay, this is very true. Now, when these two come together to form that ionic bond, they're going to create something in which, again, the charge is zero, that they cancel each other out. So when we write the formula, we want to consider how many positive ions and how many negative ions are going to be necessary in order for that to occur. So we see that sodium is +1, chloride is -1, and we see that because this is +1, this is -1, they cancel each other out already. So that means we only need one sodium to cancel the charge of one chloride. So the formula is just written as NaCl. Let's try another one. So here's magnesium oxide. Now magnesium oxide, magnesium, because it's a metal, has the 2+ charge. Oxide, which is the most common ion of oxygen, has the 2- charge. We see this is 2+, this is 2-, and again, we need to adjust the number of either magnesiums or oxygens or both, or oxides, excuse me, so that the charge adds up to be equal to 0. We see that this already adds up to be equal to 0, so that means we only need one magnesium for one oxide, and therefore there's the formula of this particular compound. Now, let's try a compound in which the charges are different. For example, if we had aluminum, let's say iodide. Okay, aluminum iodide. So aluminum is a metal. We can see that by looking at the periodic table. And it has a 3+ charge for its most common ion. In fact, it's really only a common ion. Iodide is I-. And we can see that putting these two together, that the 3+ charge on the aluminum and the 1- charge on the iodide will not cancel each other out. So that means in order for this to be neutral, it's going to require an adjustment in the number of aluminums or the number of iodides. Well, obviously we would need 3 iodides in order to balance out the charge of the 1 aluminum. So that the formula of this compound should end up being Al, and adjusting the number of i's to 3 in order to balance that charge.
You can literally think about it as a balance. So if you have an actual balance, on one side you have and the other one 1 aluminum and 1, 2, 3, not oxygens. Let's make sure that you guys can see that.
In order to balance that out, as Mr. Walsh was saying. So you can almost look at it in terms of masses on a scale. It's a very similar kind of concept. In order for this to be balanced out, because this has a mass that's 3 times the size of this mass, we obviously need 3 of those in order to scale that out or balance it out. But instead, it's a matter of charge in this case. But it works very similarly. Okay. Now, let's try something like this. Iron 3 sulfide.
Now, why do you have that 3 in there?
Well, I'll tell you why I have that 3 in there, because iron is a multivalent metal. Generally, the metals in the middle of the periodic table can have more than 1 charge. And to differentiate this iron, iron 3, from the other iron, iron 2, we differentiate that with the Roman numeral. And that means that it has an F, it's Fe with a 3 plus charge. Sulfide is the ion of sulfur, which is S2 negative.
Now, if that multivalent, that term confused you, you can sometimes have iron in a 2 plus state in the same way, in this example, you can have it in a 3 plus state. You can have the same ion or the same element have different what they call oxidation states. So with these metals, remember that middle of the periodic table, you're going to need to indicate which state it is by this Roman numeral.
Exactly. Exactly. Okay, so we see that the iron here has a 3 plus charge, the sulfur here, or the sulfide, has a 2 negative charge. This is a little bit of a challenge to try to figure out how many sulfurs and how many irons we would need in order to balance this out so that the positive charges and the negative charges cancel each other. Well, it's not a huge challenge. If I had 2 irons with their 2 plus charges, or 3 plus charges, and 3 sulfides with their 2 negative charges, we see that we'll have a total of -6 here, and we'll have a total of +6 here, and so that means we would need 2 irons and 3 sulfides in order to make sure that the charges balance each other.
If this way is confusing to you, another way that you sometimes teach drawing or writing ionic compounds is the crisscross method. So if I have an iron 3 plus, all right, and then I have sulfur anion with a minus charge. Pass me the black. There you go. You would crisscross the charges. So you literally crisscross the charges and you write them below. I would then write this as so whichever method works for you, kind of thinking of it as a balance or thinking of it as a crisscross, remember, opposite charges attract, opposite charges cancel each other out. That's what makes these bonds.
Now, Mr. Walsh, while you're up there, can you show them how to do it if there's polyatomic ions involved?
Polyatomic ions. All right, which one would you want me to do?
Let's try, how about, let's try magnesium hydroxide.
Magnesium hydroxide, okay. With magnesium. Magnesium is going to have, being a metal, it's going to give up its electrons and have a 2 plus charge. Now, table of common polyatomic ions, once again, this is another thing that you guys should commit to memory before you even walk into school on that first day. Hydroxide, polyatomic ions means poly, there's multiple atoms, polyatomic, and they have a characteristic charge. This hydroxide is a group together that has a charge of -1, okay? So when I write OH, you're going to identify that as one of the polyatomics that you've memorized, and you're going to know that this group of atoms has a -1 charge. So we're going to have a -1 charge right here. Now, I treat this common polyatomic ion as one thing. This is one thing, okay? Now I'll leave that there for now, but in the year when we're working through problems, I'm not going to be making it separate and distinct like that. You're just going to have to know that that's a common polyatomic ion. Now let's do that same crisscross. Now, how many hydroxides are you need to balance how many magnesiums? I'd write this new formula as now, if it's just a 1, you don't need to put anything. For now, I'll put a 1 there. I'm going to erase it later. For now, I'll put the 1 there. Now, when you have more than one common polyatomic ion, you separate it with a parentheses. And there is 2 hydroxides. So the final formula is going to be, for magnesium hydroxide, it's going to look like this. Now I'll draw it out the other way that we were showing you with the balances. You're going to need either way, crisscross or balance. This is going to be the resulting compound for this group of charges.
Okay. Now, remember, as Mr. Walsh was saying, you don't really need to write the 1 in here, and that's because if you write magnesium once, it's understood that there are 1 of them. And again, the biggest reason why you want to put the parenthesis around the polyatomic ion when you bring that number down as a subscript is because of the fact that, as he showed before, that OH consists of only one O and one H. If we wrote it without the parenthesis, you would think that it's one O and 2 H's, which would be incorrect, because OH consists of only one O and one H. And so that's why there's the need for the parenthesis. Okay, that's writing formulas. Now let's quickly teach you how to name them. Naming is much simpler. All right, well, according to Mr. Walsh, and I have to tend to agree, I think we're going to cut this video because it's getting a little long, so we're going to cut it right here. We're going to show you naming.